Alrighty, here we go. Moment of inertia of a rod about its center of mass. The center of mass is indeed special in this context. The center of mass moment of inertia that maximizes the moment of inertia is a special thing that we can make use of with something called parallel axis theorem later. It's a very handy concept, so we will talk about it in more detail. All right, we want to set up a coordinate system around here, so I'll set it up with x and y this way, and as with the previous video, I will be setting it up with z being right around here coming up towards us, and we will be rotating around that z-axis. All right, so if we have a rod, it's really skinny. It basically just has a length to it. It would be really skinny like this, just a length. We want to divide that up into pieces where all of a single piece is the same distance from the center of rotation. In this case, that's going to look like taking and chopping it up like a piece of salami into these little slices. And we're going to choose one of those slices and call that our representative dm. All right, now I set this up with the xy coordinate system to make things easier. And that means the distance to it would just be along the x-axis some distance d, and the width of that piece would just be dx. It's very skinny along the x-axis. The whole rod we're going to think about as being uniform, mass m and length L. So we're going to have a uniform rod of mass m and length L. These are the simplest possible cases, the uniform cases. All right, if it is uniform, that gives us something special. If it is uniform, we can just write m over L to get the density. And that will always be equal to dm over dl, where now we have to identify what is our dm, what is our dl. We've already figured out our dl. It's actually that dx. We've also figured out what our r is going to be. So moment of inertia will be x squared. Well, let me write out the original equation first. I like to do that. It will be r squared dm, which in this case will be an integral over x squared. If we rearrange this, dm is m over L dx. So we'll have m over L dx. All right, limits of integration. This is super important. This end is located at minus L over 2. The opposite end is located at L over 2. That's relative to this center of rotation. We have to keep that. We have to have the minus. We have to have the L over 2. So we'll be integrating from minus L over 2 to L over 2. That can be simplified because it's a symmetric integral. You can rewrite that integral as 2 times the integral from 0 to L over 2. Be careful because you can't always do this. We can do it in this case because we're integrating a square. It's going to end up having the minus cubed, so we'll have a minus minus when we go to subtract, so the two things will end up adding up. If you had just an x and you were integrating it like we did for center of mass, maybe you don't want to think about this. All right, let's see, m over L x squared dx 2m over L integral of x squared dx 0 to L over 2, and that will be 2m over L x squared over 2 evaluated in our limits. So it's going to cancel the 2 there. All right, we get m over L times, oops, I have made a mistake. Well, it's not serious enough for me to undo the whole thing. So I made a mistake with my integral there. We're going to fix the mistake. Integral of x squared is x cubed over 3. That's kind of an important difference. All right, so 2m over L x cubed over 3 evaluated between 0 and L over 2. All right, so we can't cancel anything in that case, but we can substitute n oops, I want to write this as 3L, then we'll have L cubed over 8, because L over 2 cubed, we've got L cubed on the top, we've got 2 cubed on the bottom, and 2 cubed is 8. Now we can do a bit of cancellation. All right, oh, one other thing we can cancel, there's that. So we get ml squared over 3 times 4 is ml squared over 12. The center of mass moment of inertia of a rod that maximizes its moment of inertia is 1/12 ml squared. Okay, that is the simplest example. We're going to be doing the ring next, which is the next simplest. Then once we understand what the ring is telling us, we'll move on and do the disk and the Wesher case. After that, we'll talk about how moments of inertia can be added to each other. So you can take the moment of inertia of a small piece of your whole shape, figure that out, and then add all the individual moments of inertia up. We'll use that to do a sphere using the disks that we've already figured out. Then we'll talk about parallel axis theorem and use that to do something like a piece of paper, something that's sort of a planar shape. Got quite a bit still to do here, but that's going to do it for this one. I'll see you in the next one.